For the first of these two talks, in this session we're going to have Yaron Singer of Harvard University speaking about limitations and possibilities of optimization from samples. Yaron, thanks for coming.
Thanks, Bobby. So thanks, first of all, for organizing this workshop. It's really wonderful, and it's just always great to be back in Berkeley. So what I'm going to talk about is joint work with Eric Bolkonski, who is, where are you, Eric? Is here. And Aviad, is he here? OK, he probably already knows what I'm going to talk about. But if you guys have any hard questions, you should find these guys after the session. OK, so what I want to talk today about is basically what I think a lot of people in this audience think about, certainly a lot of people in my home community of algorithmic game theory think about. And this is kind of this interplay between machine learning and optimization. And I want to start with this really simple example that conveys this, this kind of intersection. So when I try to decide how to route from my office at Harvard to MSR or MIT, then what I usually do is I would pick up my phone and I would look for the fastest route from the destination to the source. And when I do that, what happens is basically my phone calls Google Maps or Bing Maps in this example, okay? And basically does two things. It performs some kind of execution of machine learning and execution of optimization, okay? And here's what I mean. So first of all, what happens is this application is going to try to learn a model, okay? And in this case, the model is a directed weighted graph, okay? So what happens is it maps the intersections as nodes, okay? The edges are the roads in between them, okay? And then what it does is it fits weights that describe the congestion from one road to another, okay? It's pretty straightforward. And once that's done, okay, comes an optimization algorithm that looks at this graph as if this were the ground truth, okay, and finds the shortest path. Okay, and so basically what happened is we start with data, okay, about how people are driving. We fitted a model using what I call machine learning, and then there was optimization to make what I call a decision, okay? And what's nice about this is that basically this kind of, in this case, this shortest path example is pretty robust to errors. So if we have small errors on the way that we learn these weights, these congestions, okay, it's going to translate into small errors in the decision. Okay, we may end up choosing a different path than we would have had we known the true congestions, okay? But the difference in terms of cost is going to be minimal, okay? We're going to be small. Another example that I want to talk about is this one that I really like about influence maximization in social networks. So this is where you try to decide who to select so that you're maximizing the spread of information in the network. Okay, so let's zoom in on this a little bit. So this is a network or a graph where I just didn't draw the edges, okay? And the individuals, the people, are these nodes here in purple. Okay. So basically, what happens in these in this kind of an example is that we think of this the social network as basically a way to transmission information. We can fit a model by selecting a subset of individuals. We have the edges between them, which are the friendships. And then what's interesting is that we have a model for the way that people transmit information from one another. Okay, there are different models. One model is something like independent cascade, where you're assuming that there's a probability on each edge to transmit information. Okay, so saying that this probability 0.3 means that with probability 0.3, this node transmits information to this node. So this is actually a directed model, but I'm just using an undirected graph here just for simplicity. Okay. And then what happens is when we have this model, what we want to do is we want to make a decision, okay? And the decision that we want to make is basically who to select so that we're maximizing the spread of information in the network, okay? So think if you have a, if you want to advertise the new iPhone, you have like 10 iPhones to give. Who should you give these 10 iPhones to so that you're maximizing the adoption of iPhones in the network? So what happens is, again, the algorithm looks at this network as if this were the ground truth and makes a selection. So again, what we do is we start with data, okay, where we basically learn some model, okay. And then once we've learned the model, we have an optimization step which we select the individuals that we're going to give the iPhones to. Okay. But what's interesting is when you look at these kinds of examples, then you already see that really small errors can really trick the algorithm. Okay? So what do I mean? So let's assume I have some sort of long path in the network, some long chain. Okay? And let's assume that these people communicate really well with one another. Okay? This is contrived, but this is going to convey the point. Okay, so they all transmit information with probability 1. So when I select this node, the expected number of nodes influenced is going to be on the order of n. Okay, let's say that n is the length of the network, or sorry, the length of this path. Now let's say that I have a really good machine learning algorithm that only has some sort of epsilon error. Okay, so basically what happens is it's going to, in this case, I want to say that I have an error on every edge. Okay, so now when I look at the influence of this node, it's just going to be a constant. So the problem is that if I have these long chains in the network, okay, then this is really going to fool the algorithm. Because in the true model, really it should have selected this node on the left. But in the model learned from data, it's going to say, well, you know, this node only affects a constant number of nodes, so maybe I don't care about it as much. So the ratio between the nodes that are actually influenced and the nodes that are going to be influenced is going to go to infinity.
Epsilon is like 1.8.
So here I'm just saying that epsilon is a constant, but it can be lower than a constant. Okay.
So Yaron, that's not quite the same, right? I mean, your ratio there is asking about how far off my estimate is from the truth. But that's different than saying that my actions are going to be far off from the optimal action, right? So I could have a model that's not estimated correctly, but still take decisions that are reasonable, for example. So.
Okay. Okay, good. Let's hold on to that thought. Okay, but what I'm just saying is let's take a naive algorithm, right? That's looking at this as if this were the ground truth, right? Then this is the consequence of that. But you're right. Maybe that doesn't have to be the case. So we should talk about that, right? Okay, good. Okay, sorry. So basically, when we're thinking about optimization, right? When we want to say optimization from data, then we should really think about what's happening in this model, or kind of what's happening to the data generating this model. So basically, I want to go to thinking about a data is samples of a function. A model is something that creates a surrogate function. And at the end of the day, we want to make a decision, which is an optimization step. Does that make sense?
Over F tilde.
No. So that's exactly the point, right? Does that make, right? So on both ends, we have some sort of generative model, right? Some sort of function that generates the true data, right? We can learn something, which is going to be some sort of approximation of this function. But at the end of the day, we want to make a decision on, evaluated on the true generative model. Okay. Okay. So the question is, right, when can we make reasonable decisions from data? So I want to begin by talking about saying a few things about optimization from noisy models to kind of give the motivation for what I'm going to talk about, which is optimization from samples. So basically, I think the roots for this question were already asked, well, I guess back in the 70s and 80s, but kind of closer to the things that we're thinking about. This was, so Harvey and Melkon phrased this model called PMAC learnability. Okay, so what's PMAC learnability? This is, I have a function, and I want to learn that function. And I want to, and because I'm faced in a learning scenario, I'm observing samples, so I'm going to learn it somehow approximately correct. Okay, so I'm going to learn it with I can learn with some sort of 1 plus epsilon error. Okay, so this PMAC learnability, right? What it says is I want to basically, when I observe a polynomial number of samples, I want to have an algorithm that generates some sort of surrogate function, so that with some, constant probability, the what I have is I have a function that approximates the true function well. Now this is just a natural generalization to the famous PAC model, okay? And we can use this kind of thinking, right, to say what does it mean that a function or a model is learnable. And basically, there are broad classes of functions that are what's called PMAC learnable, maybe under some distributional assumptions, okay, and obviously some assumptions about the classes of functions that we can learn. But this is something that we understand reasonably well. So the question is, now that we have this notion of PMAC learnability, can we optimize functions from data? So what we can do is we can think about what we call an epsilon erroneous oracle. And we can ask, suppose that you have an epsilon erroneous oracle, right? Meaning that instead of a true function, you just have an epsilon approximation of this function everywhere. Does that mean that you are going to be able to optimize your function? So here the answer is no. You can show that very simple submodular functions, okay, that are almost additive. Just a sec. Okay. When you have these epsilon errors that are very small constants or even things that are subconstant, you'll not be able to get any reasonable approximation for maximizing the function under cardinality constraints. Yeah, there's a question?
This seems to be stronger than what you had on the previous slide.
That's right. It's stronger, right? It's stronger because we want to ask, well, because it's a lower bound, right? So you want to say, if I have these stronger assumptions, am I able to optimize the function? And the answer is no. Even if I have these stronger assumptions, I cannot, in general, optimize these functions. Yeah, Bobby.
If I wanted to express the hardness of approximation as a function of the cardinality constraint rather than the size of the universe, is it k to the 1/2, or does it become almost linear in k?
Yeah, so here, the usual suspect, right, is like k is square root of n. But this will also happen with, like any, it doesn't have to be square root of n, obviously. It can be lower. I'm not sure it can be log n, but. OK, but in general, this is, right, we have this inapproximability. So, OK, but this assumes that the errors are somewhat adversarial. So you can ask what happens with noise. And a natural definition of noise is one where instead of having an adversary choose the error, you have this error being generated by some sort of distribution. And in this case, what you can show is basically optimal guarantees for this problem of optimization under cardinality constraints. Okay. So this is actually a good point to pause and say that everything that I'm talking about is combinatorial functions today. But pretty much everything that I'm saying has its natural analog in convex optimization. Okay, some things. Usually, what happens is that things are kind of more technically interesting in the realm of combinatorial optimization. Okay, but for example, what I just said about lower bounds for erroneous oracles, this also applies for convex functions. And this result is easy for to show for convex functions, but somewhat difficult for submodular functions. Yeah.
Can you just say what is the condition on the distribution D?
OK, right. So different conditions will give you different things. If you want, for now, you can just assume that the distribution is bounded. Otherwise, you can have essentially you can define this somewhat artificial class of distributions, but this class of distributions kind of most classes of distributions that you think about will be in this distribution, and this result will hold.
Is IID over the different sets S?
Yeah, and everything is IID. You can show these nasty lower bounds for correlated distributions. Basically the adversarial result is for correlated distributions. You can show other lower bounds for simple correlated distributions. Basically, this is kind of what I think we can hope to get. Yeah.
Is your approximation algorithm agnostic to the shape of the noise? Does the algorithm designer need to know the distribution D when?
No. It's agnostic to the shape of noise. Doesn't need to know the distribution. The reason why it's hesitating is because there's an issue of how many samples. There's a smoothing part, and then there's a question of how many samples do you need to do for smoothing, so you can define if the distribution is bounded, then you're fine. Okay, so, but
So you need to know some complexity parameter of the distribution.
yes,
If you have an upper bound on that parameter, you're good to go.
yes. Okay, but this is not what I want to talk about. Okay, I mean, I do and don't, right? What I want to do is I want to kind of present this as motivation for what I really want to talk about. Okay, so why am I telling you this? Well, I'm telling you this because you're looking at, we have this. We have functions, we know that they're learnable, right? And now we're asking, can we do something from these functions that are learnable from data? And at this point, it's a mixed, it's a bit, we know that if the errors are adversarial, then the answer is no. But maybe these errors are not adversarial. Maybe they fall into this category, right? Which is good, which we can optimize them, right? And maybe your algorithm, and maybe it's the case that your algorithm, the errors don't fall into this category, but but maybe there's a different learning algorithm where the errors would fall into this category. So instead of asking all this, what we need to do is we need to basically just lose the middleman. We need to look at data and see if we can make a decision. Does that make sense? We need to look at the input of as algorithm designers, we basically need to look at the input of the machine learning algorithm as if that's our input, okay? And from that, just be able to design our approximation algorithm, okay? So this is optimization from samples. So now you can ask me questions. All right, so what's the model? Really, I don't think that there is much of a model here, but it's what I said. There's, basically there's the input to the machine learning algorithm, and you're trying to optimize it. So, but okay. Nevertheless, you see a distribution over sets and their function values, and your objective is to make a decision, which is to maximize your function under some constraint. Okay, and everything that I'm going to talk about is just going to be cardinality constraint. You can think of more complicated constraints like matrix constraints and other things, but for the purpose of this talk, everything's just going to be cardinality constraints. Okay. And now, what are we going to assume for making this problem interesting? The first thing we're going to assume is that the observations are feasible. If they're not feasible, it's really easy to show these impossibility results. All your samples are coming from sets of size 1, and you're now asked to optimize sets of size square root of n, right? And you have a square root of n lower bound. That's not surprising. So we're going to assume that distributions are over feasible sets. Okay? The second thing that we're going to assume is that this function is statistically learnable. We can talk about functions that are PAC learnable or PMAC learnable. Okay? And the reason is because intuitively we think that we should be able to find positive results in places where the functions are somewhat learnable. Okay? And finally, this is a no-brainer. The function should be optimizable, because if it's not optimizable in the sense that if there's in the value oracle model, right? If you should be able to query if you query a set, get the function value, right? Then in polynomial, and that takes you in polynomial time. Then basically in polynomial time, you should be able to optimize your function, right? Because somewhat, if that doesn't happen, then you shouldn't be able to, expect to optimize your function when you have less information. Okay. And the question is whether we can optimize things from samples. So the main result is the answer is no. We show that there are functions that are heavily used in practice, that are learnable and optimizable, but to which there's no constant factor approximation. Okay. And what I want to do is I want to talk about this impossibility result. I'll give you this very high-level technical overview. And then I'll talk a little bit about possibility results and just conclude. Okay. So this is maybe a good time to take questions about the model or.
Okay. I didn't understand the assumption about the distribution over SI. If you only assume that it's supported on the collection of feasible sets, it sounds like you could. If the feasible sets are all sets of cardinality from 1 up to k, I could still give you a distribution supported on singletons.
Sure.
be contained in the feasible set.
But not any distribution. There are distributions over singletons. So the question is, well, what is our notion of universality, right? Like for the lower bound, right? So one notion is to say, for all distributions, I can show you that you're not, there's no distribution under which you're going to be able to optimize from samples, right? Which is what we're showing, no feasible distributions. Or, right? We can say, we can talk about, or we can kind of look at the orthogonal, or we can look at the kind of like the orthogonal direction, which is going to ask to remove this assumption about observations being feasible, right? And then we would need to, for the lower bound, we just need to show that there exists a distribution, right, for which we have an impossibility result. And both things are, and the result holds for both, like both perspectives, if that makes sense. No?
I think what he's asking is if you're trying to optimize a function of k and all your samples are of size 1. So
Yes.
we won't be able
So then there's a trivial, right? So then there's a trivial, then there's a trivial lower bound, right?
Wait, let me
Sure.
rephrase my question in a much more obtuse way. Assumption number 1 says that a distribution equals a set. So my type checker rejects your slide because the left-hand side has the type probability distribution and the right-hand side has the type set. Are you just, is
sorry.
Is D the uniform distribution over sets of that size?
D is a distribution. For simplicity, yes. Okay, but in general, no. It can be any distribution over feasible solutions.
Oh, your lower bound has a for all quantifier
Yes.
over D.
Over any, yeah.
Good. Okay. Thanks.
Okay, sorry. This is not a good way to write this.
That's just the support.
Data specified? I mean, do you have like a black box which has this distribution and every time you like sort of draw a sample from it and do something, or is it given like a fixed number of samples from this distribution?
So I'm assuming that somebody generates these samples, right? From and all my assumption is that these samples are coming from a distribution, but I don't know what that distribution is necessarily.
But can your algorithm sort of adaptively sample from?
No. Okay, good question. No. So if I could adaptively sample, then I would be in a value query model where I know that I'm able to optimize a wide range of functions. Okay. So what goes into showing this inapproximability of coverage functions, which is the class of functions that we show the lower bound for? Okay. So first of all, I should define what a coverage function is. Okay, so I drew this little picture here, and basically a coverage function is when you have elements in some sort of universe, and you have sets that cover these elements. The coverage function is basically when you take a union of these sets and you look at their cardinality, then that's the coverage function. Okay. And coverage functions are nice. They're heavily used in machine learning, data mining, mechanism design, and other things. So the influence maximization example that I gave is actually basically a generalization of a coverage function. We know that the greedy algorithm gives us a 1 minus 1 over approximation, and we know that that's optimal. And we know that they're PMAC learnable. So Vitali here with Pravesh Kothari showed that they're PMAC learnable with an efficient algorithm when we have uniform distributions or product distributions. And Bobby with Ashwin Banandiuru, Shachar Dubzinski, Hufu, K is for Bobby Kleinberg, N is for Nissan, and R is for Tim Roughgarden here, showed that was impressive, showed that coverage functions basically are PMAC learnable within any factor 1 minus epsilon, but without giving an algorithm. But at least information theoretically, we know that they're PMAC learnable. And also, there are somewhat canonical examples of submodular functions. So if you kind of want to think about what is a nice function that kind of describes the what makes the intricacies of some modular functions, then coverage functions are it. We have other nice properties that maybe I'll talk about later. Okay. Right, so our lower bound says that there's no constant factor approximation for basically optimizing coverage functions from samples for any distribution over feasible sets. Okay, so maybe I should have had that slide earlier. Right, and some the implications of this, right, are that essentially for many real world problems that we care about in the real world, I don't know if they're real world problems, but they're problems that we claim to care about in the real world. We know that there's basically no provable guarantees, right? It may be that we're learning functions and then we know how to optimize them, but essentially, we could argue whether it's meaningful to do that, right? It says also that basically the fact that we have something that's learnable and approximable doesn't necessarily imply that it's optimizable from samples. Okay, and or the way that I tell this to my mom is that basically predictions can be easy and decisions can be hard. Okay. All right. So how do we show an approximability?
Just a question more. It still seems to be that you could be in the situation that for any distribution, there is some part of the domain over which you just don't learn anything, and therefore you will not be able to optimize for some functions. Or once you fix the distribution, you can pick a function for which you won't see anything sort of useful to be able to optimize it. But then, I mean, in some sense, since you have already the distribution, you could say some things are more natural than others. Maybe all you care is to be better than 1 minus some alpha fraction of all the points that you observe. You don't want to find the true maximum, but you want to be better than anything that you get, like some sort of large fraction that you have of things that you observe. Of course, if you just polynomial it, you could do it in polynomial time, but maybe you could do something better than that. What I mean is because some inputs are more natural than others, because you assume that there exists a distribution. You could try to define maximization relative to the distribution too.
Yes. Maybe I'll talk about that in the end, but the problem with notions like that, I think that's a very good question. So if I understand your question correctly, you're asking, well, I'm going to paraphrase here, okay? In learning theory, right, we learned that there's no reason, there's no way that we should be able to, learn a function on a different distribution, than what we've seen. So why would this make any sense for optimization? Is that roughly?
In that direction.
Okay, so here are two things that I want to say about that. I think that's a very good question, and we're certainly thinking about this, right? So two things are, well, one of the things is because for when you enter this world as somebody who comes from optimization, then you don't care about what people learned about in learning theory, right? In the sense that you want to optimize the function, right? That's what that's what you want to do, right? And with influence maximization, right? Thinking about how to optimize a function. So, what does it mean that I know? What does it mean that why do I care now that functions are submodular if there's no way that I can actually optimize them from the data that I've seen? But a more technical answer is that we could look at alternative notions of optimization from samples, where we're looking at basically we're learning a distribution. We're learning a function over one distribution, then we want to optimize over another, and then we basically want to kind of get a good average approximation over that same distribution. If we do that, then basically what we're looking at these, basically we're looking at properties of distributions. We're looking at essentially how well we can approximate the maximum from a distribution. Does that make sense? We can talk about this more offline or at the end, but basically you can basically kind of find you can define a function which is the constant function and that's basically going to be good enough for optimizing over a data set drawn from the same distribution. And one could argue that maybe the constant function is not something very meaningful to optimize over. Okay? But we can talk about that. OK, but sticking to this notion of optimization from samples. So what goes into why should, how do we show a lower bound, right? So the first question that we should ask ourselves is like, why should there be a lower bound, right? If we think about standard lower bounds in optimization, there's the value query model, right? And basically, the way that we show lower bounds in this value query model is we construct two functions. Here it's going to be f and h. And basically, h is going to kind of grow a little bit, and then it's going to level off. And f is just going to be a function that continues on growing. And essentially what happens is that we say, look, exponentially many queries, these functions are going to be the same, right? So it's going to be hard to distinguish between them. And then we get this gap between them. And in the value query model, the gap is 1 minus 1 over e. Okay. So what's different in optimization from samples? So one thing is you want to create exactly this kind of effect, but so that exponentially many samples now are going to fall into this region where things look exactly the same, right? And then you have one function that levels off and then another function that continues on growing. But now this gap has to grow from 1 minus 1 over e to n to the should be 1 n to the minus third. Okay, so now the gap needs to be huge. So somehow the fact that we're looking at samples, right, makes this gap grow by a lot. Okay. The second thing is for coverage functions, you just don't have this property that they level off so nicely. So for coverage functions, what happens is that the functions have some sort of curvature. Am I out of time or?
A couple minutes.
Okay. A couple minutes out of time or?
You have a couple minutes to go.
I have a couple minutes to go. OK, good. OK, so now the approximation gap is n to the. Wait, don't I have like 15 more minutes, Bobby?
Sorry.
Isn't that like the nightmare of the audience?
My mistake.
OK.
I thought it was a half-hour time slot. My mistake.
OK, no. OK, good. All right, so I'll give you the extended version.
Wrong decision.
Yeah, wrong decision. Yeah, it's not an online algorithm. You decide in the beginning, and you lost. OK, so now we need to show that the approximation gap is just going to decrease a little bit. OK, I'll make you a deal. 10 minutes. Okay.
I have no bargaining position.
OK, so to show this lower bound, so let me just give you 5 slides on how to show this lower bound. OK, on what goes into this lower bound. So this lower bound is in a class of coverage functions. OK, they're defined by basically there is a partition here, T0 to Tm. It's a partition of the ground set. And now these functions are defined based on the partition. And they're basically sums of coverage functions, which we call good functions that have high value and bad functions that have low value, which is, OK, shouldn't be surprised. So what we do is basically, the first thing we do is we reduce this question of optimization from samples to properties on these good and bad functions. So now what we do is we say, OK, if we have good and bad functions that respect these 3 properties, then we give you a lower bound. OK. So then what we need to do is we need to define these good and bad functions that have these properties. OK, so to do that, what we do is we define these class of primitives. These are particular coverage functions that have these nice properties that we prove in the third part. And then we get a lower bound for coverage functions with when distributions are drawn from, when the samples are drawn from the uniform distribution and when the universe is exponentially large. So then we just remove these 2 assumptions. OK, so what are these properties that the good and bad functions need to respect? So they have 3 properties. Basically, they need to be identical on small sets, like I showed in the drawing. There needs to be this large gap, on larger sets. And finally, what we need to have is we need to have this curvature property of the good function. Okay. So the first thing we show is we show a theorem that says, okay, if you have good and bad functions that have these three properties, then we can give you a lower bound as a function of these properties. Okay. So how do we build these good and bad functions to have these properties? So what we do is we have this class of primitive, these coverage functions that respect the identical in small sets. They have this alpha gap on large sets, and then they have this curvature property for the large sets. Okay, so how do we think about this? So what we do is we define these good and bad functions in terms of these primitives that I haven't told you what they are, and I'm not going to tell you what they are. I'll just kind of sketch them out to you. Okay. But what we do is we kind of we put this in some sort of as a system of linear equations, where every column here is the function values for sets of size 1 through L. Okay? These functions are symmetric. And then both the good and the bad functions are defined as convex combinations of these coverage functions. And the good function also is defined in terms of this y. So to get this property of being identical in small sets, what we do is we basically show that, that when we put these coverage functions in this matrix form, then this matrix is invertible. Okay? Then we get this property of being identical in small sets. And then we show that these, when we show that, that these multipliers are bounded, then we can show this curvature property. Okay? So what it ends up boiling down to is how do we construct these special primitives, these special coverage functions that have all these nice properties. Okay? So I'm going to let you look at the paper. Okay? But basically what they are is we define them in terms of the binomial distribution. Okay? And then to show that the matrix is invertible, we give some sort of polynomial interpretations of these functions. And then we show that the coefficients are bounded. We use Hadamard's inequality. Okay? This is kind of these are the technical details that I'm kind of putting under the table here. Okay, then finally, there are just like 2 more steps. Okay? We need to kind of make these coverage, instead of having exponential universe, we end up having compact representation. So we basically do this with like KY's independence. So again, this is kind of like the more technical aspect, so you can look at that in the paper. And then finally, we go from having everything defined on the uniform distributions to we can show this holds for any feasible distribution over feasible sets. So putting all this together, we get a lower bound. We get that for any distribution, coverage functions cannot be optimized from samples. The approximation, then approximabilities are n to the -1/4 when we have exponential size representation universe, and when we have compact universe, which is polynomial size, then we just have something that's non-constant. So this result is, also applies to the case where you actually know exactly what the sets are, okay, but you just don't know the weights, okay. And basically, this is what I told Bobby earlier. You can kind of alternate between saying that if you don't want this kind of result over feasible solutions, you can have you can have this an approximability result for uniform distributions over any sets. Okay, so in general, for other classes of functions like XOS, we can show tight bounds, and the upper bound, we have an upper bound of n to the -1/3, and that applies to any submodular function. Okay, so this is all the bad news. So now here's some good news. So I'm going to talk about some positive results. Everything that I'm going to talk about is for the uniform distributions. So for additive functions, which is a special case of coverage functions, you can show that they're optimizable from samples. How? There's an algorithm that you can basically use to recover the function value exactly, okay, after polynomial many samples, and then you can optimize the function. Okay. So basically what happens is that additive functions are what we call recoverable, right? You can recover the function valued with an arbitrary precision. So a natural question is whether optimization from samples requires the function to be recoverable. And the answer is no, because you can look at unit demand functions. And unit demand functions, you can show these ridiculously simple examples showing that there's no way in the world that you'll be able to recover the function, but they're really easy to optimize from samples. Okay? So this optimization from samples is a notion which is, weaker than recoverability.
So is this basically because you don't need to recover the function value at points that are very far away from the max? Is that?
No, it's even simpler than that. You can just basically, okay, so here's the example. Think of like half of your elements are, have value 1, half the elements have value 0. You now see random samples of, sufficiently, I don't know, k elements, right? When k is large enough, with very, very high probability, in every sample there's going to be like a large element, right? So that's it. But you have no way of knowing which of the elements is the large one, which is the small one. Okay, so I actually gave a related talk at CMU last year. Then Avram said, this probably is not going to apply for functions that have bounded curvature. And I thought that it would, but turns out he was absolutely right. So we can show that if you're special cases when your function has bounded curvature, meaning that intuitively it's not far away from being an additive function, okay? Or you can bound how far away your submodular function is from being additive, okay? So whenever this function has curvature C, there's a kind of this weird approximation ratio, but this is justified by the fact that it's actually tight. You can show submodular functions that have this curvature and for which there's no algorithm that can do better. Okay. So there's some light at the end of the tunnel. Just to conclude, okay. So what we saw is in general, right, when we have small estimation errors that can lead to tragedies unless we make some assumptions about what these estimation errors are, right? But in general, in this case of these in terms of learnability, we don't know what these errors are, so we need to actually look at what's happening from the from the input of the learning algorithm. I think that the moral question is, what's the limitation of the optimization models that we have, right? We should kind of know what they are and acknowledge them and know when we have provable guarantees and when we don't. I think that for some of the problems that I've been thinking about, I kind of know how to identify the, let's say, to put it mildly, the cases in which I don't have provable guarantees, okay? If somebody's learning, if I'm optimizing a function that's being learned from data, but that function is very far away from from reality, then it doesn't matter that I know how to give a tight 1 minus 1 over E approximation. So basically learning and sketching frameworks, where we have these errors introduced in them, they also have the same kind of inapproximabilities. And in general, these decisions from data, in general, don't have provable guarantees. Okay, so with that, thanks.
So, how would the picture change if you went to a model with additive approximation rather than multiplicative one? So the function is between 0 and 1, but now you want like an epsilon additive approximation.
Yeah, so that's a good question. From our experience, not a lot.
The lower bound still applies?
Yeah, the lower bound still applies. So when we look at when we look at convex optimization, we look at additive approximations, and then your lower bounds still apply. Yeah, so so I should say what's going on for convex optimization. For convex optimization, it's not, it's technically much easier to show lower bounds for, essentially for piecewise linear functions. Okay, you can optimize linear functions from samples, but when it's piecewise linear, already you cannot. Okay.
So in terms of looking for other brighter, more optimistic points of light, something like, symmetric modular function?
Okay.
Like cuts? So.
Yeah, okay, that's a very good question. Okay, so one could look, kind of let me tell you what our thought process was. First of all, what we're looking at is we're looking at constraint optimization, and it's nicer to, look at unconstrained optimization, but for non-monotone functions, we know that without doing anything, right, we can get for non-monotone modular functions, we can just by random sampling, we can get a 1/4 approximation, right? So basically, it sort of takes the the sting away from an impossibility result, right? So we thought, well, if we showed impossibility showing the kind of like a separation with samples, you can only do half, but without samples, you can do like one. So it kind of like went for the, where things would be dramatic. But you're right. It could be that symmetric functions could be like a natural class of functions to look at.
So does it make sense to consider some sort of maybe in-between model? So the way I have this picture in my head is, you're trying to find the highest point on the hill, and what you have to work with are the heights of random points. And so it's kind of challenging if, the hill could have a little spike somewhere, and you didn't see that, On the other hand, you are saying it has to be reasonable in the sense that you have to. It should be that with value queries you can do something well. So that if you can actually climb the hill, you should. So on the one hand, you sort of are allowed fully adaptive queries, and then so we're going to assume that you have to at least be able to do well there, because if you can't do well there, you're dead. Sure. And then what you're saying is that if you just get these random samples, it's not enough information. I wonder, does it make sense to consider some model in between where maybe, I don't know. The model where you have some data, you can do a little bit of.
Yeah, Eric has been thinking kind of more actively than I have about exactly this in-between model, where maybe you can kind of bound the number of adaptive queries that you make. Maybe we can have like a hybrid saying that, okay, you have a pool of samples and now you're allowed to make like a small number of queries. Maybe there's something to do there. So that's a reasonable model, I think, and a very good question. So.
All right, let's thank Yaron again.